Good afternoon, everybody. This is Roger Frechette, and I'm the Managing Principal of Interface Engineering, and I want to welcome you all to the 10th installment of Interface's High Performance Buildings free webinar series. This is the 10th and last presentation that we're offering this year, 2020. We will be putting together a list of new presentations to bring to you next year. But this is the last one, and we've kept one of the best for last. So we hope that you all enjoy it. Before we get into it, I just want to give you a little overview about Interface Engineering. We are a 51-year-old mechanical, electrical, plumbing, engineering design firm. We have offices, 7 offices across the United States. Our office local is in Washington, D.C. We've been there for 8 years, focusing on many different market sectors, but we have a particular expertise in high performance design, low energy, net zero energy, and positive energy buildings. Included in that is the country's very first net zero energy K-12 school building at Hood River Middle School in Portland. And much more recently, the net zero energy school in Falls Church, Virginia, the George Mason High School project, which I believe we're going to hear a little bit about today. So today's presenter, Mr. Kevin Cahill. Kevin and I have worked together for more than 20 years now. We've been partners for the last 8 years. But Kevin is a fantastic engineer. He is a principal in our Washington, D.C. office. Kevin earned his bachelor's degree in mechanical engineering from Worcester Polytech Institute in Massachusetts. He is a professional engineer licensed in the District of Columbia. He is a LEED accredited professional. And a couple years back, Kevin was recognized as one of the top 40 engineers in the country under 40 years old by Specifying Engineering magazine. And Kevin is truly an expert in high performance school design. So Kevin is going to take us through this 10th session, high performance schools that make the grade. So Kevin, take it away.
Well, all right, Roger, thank you. You can be my hype man any day. I appreciate the kind words and introduction. And with that, I will jump right into high performance schools that make the grade and get us right into agenda and learning objectives. The course description. The course description is really meant for architects, engineers, leaders of the built environment to really look at sustainable and energy performance goals that push the modern HVAC systems and design efficiencies and building envelope efficiencies to a new level of high performance. The presentation will touch on the definitions of net zero and net zero ready, and we'll try to explain a little bit about our design approach and the design process on how to achieve those goals, along with balancing system strategies against cost, schedule, performance. And we'll walk you through 4 case studies at the end, a renovation to that are certified net zero energy and have been for quite a few years now, as Roger mentioned, and one that is currently in construction locally here in the DC metro area. So our learning objectives today, we're going to go through the definition of net zero and net zero ready. We're going to talk about why K-12 schools are really great candidates for high performance design and high performance buildings. We'll talk about the energy modeling process, what the variables are and what the focus is. And you'll see a theme start to come through in the case studies, and I'll probably point some of those themes out as we go. And last, we'll look at the application of the process, that energy modeling process and that high performance process within the 4 case studies that we'll walk through. So the definition of net zero energy. The Department of Energy, as only the government could do, has a 22-page document that they published in September of 2015 that defines the definition, a common definition for zero energy buildings. You're welcome to read all 22 pages at your leisure. When we send the presentation out, you can search for this and you'll find it on the internet, no problem. But for our purposes today, a zero energy building is an energy efficient building where as a site energy analysis, the actual annual delivered energy is less than or equal to the on-site renewable exported energy. And what that really means is, and the focus for that for this group is really, it is based on an annual basis. So you'll see trending all the way through our case studies that there are times of the year, in fact, where we use more energy than we generate. And there are absolutely times of the year where we generate more energy than we use. So we'll go through some of those things and why it's important that net zero energy is defined annually, because we're sizing our photovoltaic panels or our power generation for that annual number, not a peak number and not the highest month. So that, and you'll see that in some of the graphs, and hopefully I remember to point that out. A recent RFP that came out had some measurable high performance criteria. And I'd say we'd been using this criteria long before the RFP came out, but we think it's a good place to start. It's really a great place to start when you're looking at K-12 schools. You're targeting an energy use intensity of about 21. It's a pretty good number to start with here in the Mid-Atlantic and the Washington, D.C. metro area. You're looking at R values for the roof and the wall and under slab of 30, 25, and 10. Always thermally broken windows with insulated glass. I think you'd have to go out of your way these days not to do that. We're looking at glazing percentages for schools in the 35 to 40% range, and air tightness and building envelope tightness. And then we're always focusing on systems that are durable and straightforward and easy to operate and control and maintain. And that's going to be an interesting balance between all of those items and all of those things. And we'll go through some of that as we proceed here in the presentation as well. So why would you want to do high performance schools or net zero schools? Why is that important, or why are they good candidates for such an acclamation? So the real reason is the energy demand. The energy demand on schools, at least the existing building infrastructure, is actually quite high. You'll see from CBEX data and Energy Star data that baseline buildings or average buildings have energy use intensities that creep up into the 60s, 70s, and 80s. And that's true across the country, both in certainly where our offices are, Pacific Northwest and California, as well as in the Mid-Atlantic. So they become a good candidate because of the energy demand. And while the occupancy levels are relatively predictable during school hours, we've joked recently on our high school project that our high school projects are much more of a community center that teaches class during the day or during the weekday specifically. So we do have a lot of operating hours on a lot of these schools. Some open as early as 7 and stay open as late as 11 p.m. For those that have high school students for sure. And then the other reason they're a good candidate is, the plug loads are actually relatively low, but depending on the performance of the school, certainly elementary schools have less plug load than our high schools when we get into labs and auditoriums and higher level competition gymnasiums. The second reason that they make good candidates is it's highly renewable energy potential. Most of the roofs of our schools, many of the roofs, are available for the application of photovoltaic panels and power generation on the roof. Most of our schools, the roofs are not accessible to students for a whole host of reasons. Unless you have a school where you've built gardens or a field or a play field on your roof for specific geographical or geometry reasons, most of the roofs are available, which gives us great potential to earn energy on our roofs. All these buildings, when we talk about K-12, are owner-occupied. Owner-occupied buildings become very important because they're going to build this school and maintain it for a minimum of 50 years. I certainly know I serve on an advisory committee for one of the local counties. And, some of their metrics are surprising when it comes to the schools and how they budget for the modernizations and upgrades. And they're looking at schools that will be very resilient for at least 35 years. So there's a big investment there, but there's a payback there for a lot of these institutions and a lot of these buildings as well. So there's a good metric there. We look to schools to be a little more resilient, a little less so here in the Mid-Atlantic, but certainly all you have to do is turn on the news today and find any local storm coming through the Gulf Coast and realize that our schools, when they're hardened and when they can generate their own power, become an even better opportunity as community centers in some of that disaster recovery and better learning environment. So our high performance buildings aren't just about energy. We have improved indoor air quality, improved daylighting, improved access to views. All of those things create a better learning environment for our kids and our students and our teachers and faculty and employees as well. Let's not forget about them as we go through this process. And last but not least, schools really should have, a sustainable mission, and the schools themselves can prove and provide a living laboratory to our students, really at any level. And that starts, whether that's elementary school through high school, there's opportunities to educate our students about their buildings and about the energy consumption therein and how that works. So where would you apply net zero or high performance buildings? Where could these work? Where might they work? So the New Buildings Institute, this report's actually from 2018. The 2019 report is very comparable. I think there's only a couple of buildings that were actually added since this report. But there are 32 buildings, according to the New Building Institute, certified as net zero energy by the year 2018. Out of those, about 14 were academic buildings or academic focused. So a little less than 50% were on the academic side. And out of those, 8 of them were K through 12. So about 25%, as of 2018, about 25% of the certified zero energy buildings per the New Buildings Institute were K-12 projects. So we certainly would like to see that number increase as we move forward. And we're here to help in doing that with some of the design process and goals that these projects have. So where are these 8? So this is the map of the US showing you where those 8 are. West Coast, East Coast, Kentucky, Hawaii. You can see there's a huge land of opportunity in the middle there, anywhere between California and Kentucky. As of 2018 anyway, had a huge opportunity for certified net zero schools. So anybody on the phone that's in those geographic locations certainly has an opportunity. But you'll see there's a whole host and ranges of climate zones represented, as well as geography, weather, and access to solar power. So, or power generation, I should say. So if we can do it in all of these locations, we can do it just about anywhere. It really depends and relies on the design process. And those, so out of those 8 schools, sorry about that, out of those 8 schools, 2 of those are certified as net zero energy and were both designed by Interface. And these 2 I'll give you as part of 2 of the 4 case studies at the end here, Hood River and Sacred Heart. With, again, as Roger mentioned, with Hood River on its 10th year anniversary just this year. So how do we do this process? What is the process for us to get to a high performance building in terms of what do we really look at and why do we look at it? Space heating, pumps, fans, space cooling, lighting. As the mechanical engineer in an MEP firm, we certainly look at all of these systems on a daily basis, but we really focus on a design process. So we have a 4-step approach when we approach net zero and high performance buildings, and we look at reduction strategies, reclamation strategies, absorption strategies, and generation strategies. For those that have been part of the other 9 presentations we've done or so, I think we've gone through this in more detail in some of those other presentations. You're certainly welcome to go back either through our website or our YouTube channel and look at some of those. We even did one specific just to energy modeling and specific case study to a net zero energy commercial building. where we go through those steps in a little more detail. But all of those are applied to our K-12 school processes as well. So I'm going to jump right into the energy modeling portion of that 4-step process. So the key to all of our high performance building is the analysis, the constant real-time feedback to our design teams, to our owners about the energy modeling and the metrics of how we get here. So we generally almost always are following 90.1 Appendix G. I would say nearly all our schools, it's probably safe to say all of our schools in the Mid-Atlantic are LEED schools of some shape or form, whether they're designed to that standard or achieve it. Certainly in Washington, requirement as an example, and we're generally following 90.1 Appendix G for our performance rating when we're evaluating systems. So what's important about that is that we talk about a proposed design and a baseline design. The proposed design matches the actual design. So the actual design is what's on our construction documents. And the baseline design, for the most part, is minimally code compliant and standard practices per the design and the ASHRAE 90.1. So we're constantly comparing those two. There's a whole host of software you can use that you're allowed to use per ASHRAE 90.1 Appendix G, a whole host of different ones. We generally, here on the East Coast of Interface, use Energy Plus and Design Builder, but we certainly use all of them across our firm in terms of all the different softwares and platforms available to us. Our simulation results, generally we're using Energy Plus. We always start with the climate data. The good news for everyone is that recently, very recently, we now have readily available to us the energy and the national climate data. We have the climate data from the years 2004 to 2018. Previously, that TMY file was from 1975 to 2005, or in some cases from 1990 to 2005. So given that within the climate change world that we live in, that you have 8, 9, or 10 of the hottest years on record in the last 10 years, it's very important that we now use the latest available, readily available climate data, which gets you at least back until 2018. And it's a great average. I think that 14, 15-year average is going to prove to be a bit more challenging than the weather before that, given climate change. But the good news is that moving forward, all our energy models are incorporating that newest data or that updated data. So that's kind of important for that. And then for our energy rates, we're using the actual utility data or the state averages from DOE. So the components of an energy model are this. When we follow Appendix G, there's really 13, let's call them chapters, or 13 subsections that we focus on, both from the model and the geometry all the way down to the modeling limitations, receptacle loads, etc. But within this, so many of these, the proposed design and baseline design are required to be the same. The major items that are different, so for example, an example that it has to be the same is the space use classification and the schedules of the building. They're the same in the proposed design and the baseline design. So the major ones that can change is the building envelope is a prime opportunity for improvements, the lighting and lighting controls, remembering, of course, depending that you have to follow the minimum requirements, and there's a host of them for lighting controls, HVAC systems, and service hot water. And service hot water, for those that don't know, is really the domestic hot water system in your building, and sinks in your kitchen, etc. So the components, the major 4 components of the energy model that can move and change when you're doing a comparative analysis of proposed to baseline is those 4: envelope, lighting, HVAC, and service hot water. You're going to see that theme very consistent sort of all the way through the case studies I show you because those are the four major components that can move the needle. And not any one of them is a silver bullet, by the way. It's almost always a combination of all of those in order to get our achieved goals. So when would you apply it, or how would you apply it? So I'm going to get into case study number 1. And case study number 1 is a local elementary school. So this is Abingdon Elementary. And I say local, I should say I'm in Washington, D.C., so it's local to me. Is in Arlington, Virginia, Abingdon Elementary School. This building was originally 78,000 square feet and was expanded to 106,000 square feet. So we had a large component of an existing building with an expansion of about 33% more area. The importance of this is the application of high performance goals to existing buildings. So certainly we applied those high performance goals to the new portion of the building or the addition, but we applied as many as we could to the existing building as well, while being very mindful of budget, construction costs, construction schedule, phasing. Certainly a very complicated deal when it came to renovation and new. The sustainable strategies for this project were improved building envelope, a VRF system, air-cooled for the heating and cooling of the additional components of the building, and daylighting and controls. And you'll see that those three are very much in alignment with the four major components that you're allowed to change, or your comparative components within the energy model. The reason service hot water is not here is it was an existing domestic hot water system that was existing to remain, and we were able to, it was relatively new, so we were able to maintain that portion of the project. So that actually shows up in our model in this case as the same number. We didn't make any hot water improvements. So this is sort of a section of what that could look like within the VRF component of what we did. I don't know if you can see my arrow here, but what we have here is a dedicated ventilation air system with energy recovery, and that provides ventilation air to the new components of the building. Let's call it all the classrooms. And then decoupled from that is a variable refrigerant flow, or a VRF system, that does the heating and cooling. One thing you will notice with most, I shouldn't say all because I'm not familiar with all net zero buildings, but with most net zero buildings, you will see a decoupling of the ventilation air component to the heating and cooling component within buildings. And what that allows us to do is control both of those independently and really focus on the energy performance of each one. So when we use refrigerant piping is much more efficient at transferring energy through your building as compared to some of the older building infrastructure where you have a rooftop air handling unit, for example, that delivers all of its energy on the air side and none of it through either a water or a refrigerant side. So the decoupling is very good. It allows us to control ventilation and where it is and where it goes. It allows us to get energy recovery, more importantly, off of that outdoor air. And then it allows us to control those rooms, the temperature in those rooms separate from the air side. So you absolutely can have rooms that are in unoccupied mode with minimum ventilation for pressurization when the students are not in that classroom, be it in an elementary school when they have gym class or a cafeteria during lunch hour when they're not in the classrooms, or in the case of high schools, you will see that there's a host of classrooms that don't have homeroom, for example, and there's a host of specialty classrooms such as science, physics, biology, those types of classrooms. We're able to turn those on and ventilate them when we need them and turn down the ventilation when we do not. So this is for Abingdon, specific to the energy model for Abingdon. We did an energy model to look at where are the gains and losses, where are the heat gains and heat losses within the building itself. This is approximately a one-story school. At the existing building anyway, it had a small portion that was 2 stories. And we looked at where are all the heat and losses going. So in this case, the largest number is actually the occupancy, which, as you recall from the previous slide on energy modeling, the occupancy must be the same. I can't reduce my number of students and take an energy savings. And at 245 BTUs per person coming into the building in an elementary school, plus staff, teachers, kitchen staff, etc., it's a relatively large number of people in the building. You know, you could look at, 50 kids equals about 1 ton of heating or cooling, in this case cooling, because they're bringing heat with them. So I can't do anything about that. So we look at the other components of this that we can impact: the glazing, the conductive glazing, the walls, the roof, and the ventilation air. So those are the 4 components that we really focused on for this project. There was an initial reaction, I guess, from the public and a desire on this project to replace all the wall insulation because the classrooms were not performing very well in terms of temperature control. And the analysis we did really showed that it's actually, because it was essentially a 1-story building, it was really the roof load that was creating that thermal comfort issue or discomfort issue in our case. And we looked at how to improve that. So this was the roof. This building was actually built, the existing building was built in 4 phases. And now the addition that we put on and put as a 5th phase, going as far back as 1949, 1964, 1970, 1990, and now, I forget when we finished it, 2015 maybe? So 2016. So it has the multiple construction components. Thanks to our friends at Hort Copeland Mott, they had to do or did do diagrams like that in the lower left corner to really define all the different roof components of the building and what their existing performance was and what their new performance would be. And we were able to do the energy model for all of those and demonstrate that making an improvement to that roof was much more cost effective and had a larger impact on the overall building energy and thermal comfort of the building than did improving the wall insulation. In a similar way, we did the glass. So and the glass had a significant improvement. So we were able to take what amounted to really a budget for building envelope improvements, and through the 3 analysis of walls, roof, and windows, focus that money on the roof and the windows, and we largely left the existing building walls intact. And we improved a very small section of it, but most of the walls remained, so that we were able to harden the building to both that solar load in the summer, as well as all of the losses we had in the winter. So you can see, we had R values of R4, in some spaces, which were quite from 1949, and as well as 64 and 70, so that the roof insulation was quite low compared to what we would talk about today. So this is the wall analysis. Again, you can see this diagram in the lower left. I'm trying to remember, I think there's 24 different wall types in construction in the building. A lot of that has to do with, again, the fact that it was built over a series of 4 different periods and genres of time. And then certainly our new building components added another element to that by being minimally code compliant or even beyond code compliant in some cases. But within our energy model, we certainly proved that the cost of roof insulation had a much bigger impact to our energy performance than did the walls. And that's part of it. So this is the end energy use intensity. This is where all of the energy was going in the baseline model. And then ultimately, this was our countdown chart. I'm sure a lot of folks are used to seeing this. But you'll look at the baseline building. Baseline building really, and effectively the existing building, really had an energy use intensity of about 60. That building was roughly 78,000 square feet. We were able to, this model here, or this graph here, is actually if we had kept the building envelope and made these improvements, including the entire roof to R25, and the 3rd bar over where we did the high performance glazing. We then did lighting controls, lighting power density. And if we had done the entire building in a VRF while keeping the existing building envelope walls largely intact, we would have gotten to an EUI of about 29. The absorption and generation strategies were not part of the project and not part of the project budget. Now, ultimately, what happened is we had a host of existing systems in the building, just air handling units, rooftop units, et cetera, that were relatively new. And the analysis that we went through was, is it worth it? We can save you, keeping the existing equipment, we could get you to an EUI of 40, and that's kBTU per square foot per year. But ripping out all that equipment that was relatively new and swapping it out for VRF system would have gotten us to an EUI of 29. And ultimately, it was not worth it. So there was so much equipment to remove in the 78,000 square feet. We largely kept all of that existing equipment intact and had predicted an EUI of about 41. Last year, 2019, Arlington is reporting that that school actually hit an EUI of 41. So that's good. So what happened here is we expanded the building by 36%. So we have 36% more square footage. And in the process of expanding the school, we actually have an EUI that's reduced by 33%. Right, so that's pretty good in terms of the performance of the new portion of the building is quite high to overcome the dollar values of really not replacing an existing mechanical system or existing wall performance and insulation. So our case study number 2 is Sacred Heart Lower and Middle School. This is in Atherton, California. And Sacred Heart Middle School, you'll see the sustainable strategies for this included power generation, and that's photovoltaic panels on the roof. It included displacement ventilation, a variable refrigerant system, lighting and daylighting controls. In this case, natural ventilation, and we could have a conversation all day about natural ventilation and where to apply it. I know we have a lot of conversations in Washington, D.C. about natural ventilation in schools. It's an amazing climate here where a day like today would be perfect. A day like 2 weeks ago would not. So the natural ventilation here locally is absolutely worth studying what the impact could be, certainly in the Mid-Atlantic. It had indirect evaporative cooling, it had heat pump heating, it had a solar chimney, and it has 100% water recycling. So for the case of this project, it has on the roof a 42.5 kW photovoltaic system. You'll see a picture of it installed there. Schools that are 1-to-1, meaning you have a one-story school of program area to one roof area, are very, very good for net zero because you have the availability of the roof area to generate power. Taller schools with that are 4 stories, 5 stories, you start to get into difficulty where you have a 5-to-1 ratio of building program to available roof area. That becomes a different challenge or even more challenging than this. You'll see the PV performance here. Again, when I mentioned net zero, when we talk about the annual performance, you'll see in the lower left in blue the amount of PV production that we get in the summer and in those shoulder months, May, September, compared to the winter. You'll see in February and March, the measured energy consumption would exceed the generation in essentially the winter months, and the rest of the year we're able to produce, for the most part, more than we consume. And you'll see that same graph on the right. You'll see where the yellow or gold color is really showing you the production, and the black line is showing you the energy consumed. And annually, through the course of the year, we are substantially higher. So the PV prediction, the PV calculations had us producing about 50,000 kWh for the year, and the PV measured was actually 53,000. So we actually got a little bit more in some years. And the reason for that is global warming. So I think some folks will remember all of the droughts and those types of things that were happening in California. It turns out droughts are actually pretty good for energy production because we don't have as many rainy and cloudy days. But they obviously have harmful situations on the other side of the equation in terms of water. So I'm not suggesting we go to drought places, just that that's part of the reason that the predicted or the measured output was higher. The sustainable strategies included solar tubes for improved and increased natural daylight within the space. You'll see that in the library here with those solar tubes driving a lot of that light in and controlling the artificial lighting down to minimum levels. You'll see that for this project had displacement ventilation system from overhead, part of the strategy of the integrated natural ventilation was ceiling fans to keep the air moving. So this had both natural ventilation, ceiling fans, and overhead displacement system. You'll see some of that in that upper right corner right now. You see that displacement diffuser and the operable windows for natural ventilation as well. We talked about designing as a learning tool. There's an energy dashboard right in the front of the school, keeping track of all of the energy performance and metrics of the building, including the power generation as compared to the energy consumption, and letting the children and the kids take a look at all of that. This is another diagram looking at, again, that ceiling fan, the natural ventilation, and the heat recovery system overhead. The important thing, or one of the important things here, was the CO2 sensors in the space, really keeping track of all of those things to make sure that we still were maintaining CO2 levels in the building, whether we were in mechanical mode, a natural mode for ventilation, or even in a mixed mode. The other buildings on the campus had additional improvements to them and really a substantial KBTU. So the CBEX data for schools in this area is about 69. And you can see all of the other buildings reduce their EUI on this campus, 31, 23.4, and 25.1. All of them representing more than a 50% reduction compared to some of the baseline schools in the area. And last for this one is really the school is a learning opportunity. I mentioned that it was 100% recycled water. They have a stormwater collection, treatment, and reuse system for the campus that is accessible to the students. It explains to them how it works there on the glass and some diagrams, and the students are even allowed to and do take water samples and compare the water quality of the reclaimed water compared to the incoming water from the city, and do an analysis on that water as part of the school as a learning opportunity, which I think is very, very cool. It's a beautiful sunny day here in California on this picture. So the third case study is Hood River Middle School. So Hood River Middle School is net zero energy. It's located in Hood River, Oregon. It has had many, many articles written about it. This is from a presentation we gave a few years ago where they went back to the school, wrote an article and said it was 3 years in running and how well it was doing. This is an article just from this past summer in ASHRAE, and ASHRAE did a 10-year checkup on the first net zero certified net zero energy public school in the country. And 10 years later, they are telling us that it continues to meet the requirements of the net zero protocols. For this building, you'll see that it once again, we're focused on the mechanical systems, the building envelope, the ventilation. So this building actually has geothermal triple glazed windows, natural ventilation again, just like you saw in the other case. And in this case, it actually is radiant floor heating. So again, looking at following through with our procedures about looking at reduction strategies first, we focus on the building envelope, one of those things that we can control and make substantial improvements to for energy performance. You'll see where this had triple glazing, thermal mass, and brick walls. Improved roof insulation of R38, and then underslab installation of R15, which is important when you do in-slab radiant to separate yourself from the ground. So you're not actually putting any of that energy back into the ground, that the energy you do put in goes up and into your space. The PV panels, again, is part of the generation strategy on the roof. You'll see in this picture here the very tight coordination between mechanical ductwork and PV panels, which I'm sure was quite interesting. But again, the PV panels are preheating some of that air. You'll see that we're dragging the air underneath the PV panels, taking the heat off the back side of the panel, and then we're preheating the air that way before delivering it when we're in mechanical ventilation mode. It did have skylights, great opportunities, architectural design opportunities. When we talk about natural daylighting, this building actually has skylights as well as clear stories to, again, really help drive that natural light into the building and control and reduce our consumption for artificial lighting within the space. I think this is a cool use of the windows in that natural lighting in the upper right corner there. Window and rooftop ventilators. This is part of that natural ventilation strategy. Again, where you see when the windows are open, because of the way the building is designed with the pitched roof, we're allowed to let the energy stratify and actually relieve itself out in the summer. And you'll see on the right where the natural ventilation can come in, heat itself up, and relieve itself out. Very similar to what you consider a solar chimney. Again, CO2 sensors in the space monitored by the students to determine when additional outside air would be needed. So we do want to make sure we monitor CO2 when we're in natural ventilation mode to be sure that we're getting that proper airflow and the turnover of the air for the students. Displacement ventilation, again, in this case, similar to the previous project. In this case, it's displacement from the low to high. And again, the low to high here is really allowing us to stratify that air as well. So you don't have to treat that entire volume. Let's see here. Whoops. Sorry, it's stuck on the video. And then last, this project has in-slab radiant heating and cooling. You'll notice again, if I didn't mention it before, that what you'll see with this strategy is that the heating and cooling of the space is completely decoupled from the ventilation air once again. So the heating and cooling can happen through the radiant, and the ventilation is happening through either mechanical or natural ventilation. Certainly the radiant would be turned off and be off when we were in natural ventilation mode. So they are linked together, but they're not the same system. So this again is, you look at this climate data, we had a CBEX average building of about 65. We had a minimally code compliant building or a baseline building of about 46. And we had a design before renewables of 24. So we're able to still, once again, reduce that energy number down to about 50%. And then the power generation takes over from there. And then once again, school is a learning opportunity. I just thought this was a cool slide for anybody out there doing, some schools like that can incorporate, outdoor learning, or even some of the Montessori schools where they have a lot of exterior things and tactile things, and there's a lot of outdoor learning. Certainly an opportunity to do a whole host of things sustainably with water, etc. So case study 4, and I'm glad I cut slides out of this because I'm running pretty late here, but I'll try and give you the overview. So this is in Falls Church. This is currently under construction. This building is net zero energy ready. Not a lot of great definitions out there for what net zero energy ready means, but we have defined it on this project as really a project that is built to a level of performance such that with the addition of solar panels, it will achieve net zero energy performance. So with this project, the net zero energy performance of the photovoltaics is actually coming through a power purchase agreement. It is not part of the initial and first cost construction of the building. But it's a 300,000 square foot high school in the city of Falls Church. Again, this building really functions as a community center that has high school students in it during the weekday. At last count, there's more than 100 groups that use this building outside of designated school hours. And that's anything from rec league basketball to men's league basketball to Bible study on Sundays, etc. There's so many people that have access to this building and use the building, their existing high school today, that the schedule becomes a very important thing. And really getting the energy down and the energy consumption down becomes very critical, because our operating hours are substantially higher than, say, an elementary school that did not do after school programs and have French club and Latin club and those types of things, sports, drama, etc. So again, we focused on the building envelope. We had a long, exhaustive study with the architects that we worked with on this project. The building could only fit but in such a way on the site. But once we had the building situation, the massing situated, oriented, we really did study the wall insulation and roof insulation and tried to optimize that value. You can see that we picked R25 for the wall and R30 for the roof insulation, and really the total annual cost delta, if we had kept going, is quite small. We get to less than $1,000 savings annually when we improve the insulation from there. It is the case that more insulation is always better, but at what cost and at what return? So at some point, you've got to draw this line to say, okay, I'm not going to spend an extra $1 a square foot in insulation to save myself $800 a year. It really didn't have a payback. So we take that money and we apply it elsewhere to the building. So these are the summary of energy conservation measures for this building. Again, we followed that same process of reduction, reclamation, absorption, and in our case, generation for power purchase. Improved building envelope, we optimized the glazing in a similar way as that chart before. We ran through about 13 different glass types and picked the optimized performance based on cost. We have daylight responsive controls throughout the building. We have LED lighting everywhere, including the gym and the auditorium. We have switched outlets for the plugs with a vacancy sensor in the learning centers, really in the classrooms. What this is doing is it's turning off our phantom loads when the teachers are not there. So every room does have a smart display in there, and the smart display will turn off after you leave the room based on the vacancy timer sensor. In some ways, I wish I had this in my house for the kids when they walk away from the TV, but that's where the inspiration comes from, so that the monitors will not be left on nights, weekends, unoccupied modes, etc. Those monitors will turn off behind them, even if they forget to turn them off. We have a VRF system for thermal comfort that is doing the heating and cooling. We have a displacement ventilation air system. And then once again, down here, you'll see we have the dedicated outdoor air system for ventilation and energy recovery. We control that with CO2 sensors in the space. So we make sure that we are delivering the ventilation air to where the students are, and we are removing the ventilation air or minimizing the ventilation air to where the students are not. That turns out to be a big energy saver in the high school, because the buildings are quite big compared to the number of students because of all of the programs. So as students move from class to class, history, English, science, drama, gym, they're in so many different places during the day that our CO2 sensors are really tracking where the population is and keeping those levels correct. And if science ends at 2 and the school closes at 4, those spaces actually can turn down, or history or whatever, those spaces, the ventilation air can turn down to a minimum. And then we do, where am I? The geothermal system. One of the bigger moves on the project, the geothermal system is installed underneath what will be the softball field and tennis courts, largely under the softball field. And that's a big move for us, because that allowed us to not only do the heating and cooling and ventilation through geothermal, but we were able to do that service hot water, or that domestic hot water, through a water-to-water heat pump as well. And that serves our locker rooms and our bathrooms throughout the building. Whoops, sorry. So this is our roadmap again to net zero energy. And you'll see that a baseline building these days that we would have had to design to ASHRAE 90.1 2010 in DC would have had an EUI of about 46. On the left-hand side, we do all of the building envelopes, LED lighting, service hot water, the VRF system, which is water cooled, and the dedicated outdoor air system with CO2 sensors. And we get our energy use intensity down to about 21 or 22. And then we generate from there. So we have a power purchase agreement in place to generate approximately 22 kBTU per square foot per year for this high school. Some folks might say that the EUI of 22 is quite high, and I would agree. But what's really happening here is, again, as a high school that serves a community, its operating hours are quite high in terms of duration during the day, as well as nights and weekends. So that's where that number is higher than we would like, but it's really tied to and stitched to the operating hours. So this is just giving you a graph of where the reductions came from. You'll see where we're able to reduce the lighting from 20% to 12%. We reduced our gas for heating substantially by using the geothermal system. We reduced our cooling substantially, and our plug loads remained largely the same. We kept them the same in here, even though we know, as I mentioned, that we do have a system to reduce those phantom loads when the teachers are not in that space. For the generation strategies, again, this is through a power purchase agreement. We are a 7-story building, or 7 stories from bottom to top. So in this case, our roof area to floor area is quite reduced compared to that 1-to-1 on the elementary school that I showed you. So we are doing a power purchase agreement really within the neighborhood of the school, including putting photovoltaics on the roof of the high school, as well as the roof of the middle school, as well as over some of the parking facilities and walkways. So this is just showing you once again that the PV production and the energy use are, that the production is more, again, annually, but on any individual month, the energy consumption could be more than the PV production. So you'll see even in June here that our energy use is more than we can get from the PV system, and in December as well. But you can see all of those other months where, you know, March, April, May, August, July, where we're able to produce more than we consume. And that's why we always talk about high performance buildings and net zero buildings as an annual value. So this is my last slide. So for all of those case studies, you know, what was really in common? And I would say what's really in common is the project teams. You know, we are fortunate to have, from school boards to superintendents to owners to operators to facilities folks on the owner side, as well as the architectural and, you know, civil landscape teams. We've been very fortunate, I think, that the teams and the team structure is critical to making the whole thing go when you talk about high performance and net zero buildings and the synergies between all of them. So really the project team becomes very important. Setting project goals and budgets at the beginning of a job, and really trying to hold to both. Hold to those project goals as much as you can. I think a host of RFPs come out as, you know, net zero ready or net zero goal, and sometimes these projects don't get there. At the end of the day, even if you don't get there, at least you've still designed a much better building than if you just did minimally code compliant. But I think holding to those goals and budgets throughout was really key to all 4 of those case studies, really in most of our high performance buildings. The energy analysis for educated decisions, you know, in our opinion, you can't start the energy model early enough when you have a high performance building. It really helps educate, inform, and let our architects, engineers, owners, ourselves know what's happening, and really get into the numbers, get into the values of, you know, if we have a fixed budget and a fixed dollar, where do we put it and why? As in the energy model really educates the entire team on that. And then the last is having a dedicated engineering team, which of course is where interface comes in. So, and we're always committed to those goals. So with that, I know I can't open it up for questions, but I can see if there are any posted. And it looks like there are not. So if you have questions, you're welcome to send them in. You can send them in. I mean, a lot of people have my email address, but you can certainly send them in to us after the fact if you have any questions, or if it stimulated anything. I would say that, as Roger mentioned, this is the last for this series as we head into virtual learning in the current environment we live in, with all the kids being at home and people trying to balance living at home, school, kids, etc. But if you have any suggestions, if there's any topic out of the 10 that you've been to, or this one that you'd like to explore more, feel free to reach out to our office. Let us know what your thoughts were, and we'd be happy to tailor a presentation we've already did, or even do a new one if there's something you're curious about that you think would be worthy of this group of people. So with that, I don't see any questions coming in. So with that, I will end the presentation. Thank you everyone for attending. Stay healthy out there, and good luck with all your kids at home and virtual learning.
Yeah. Thank you, everybody, and we'll see you next year for the 2021 webinar series.